Hello class, and welcome to today's lecture. This is my first lecture behind the light board, so a couple of things to keep in mind. Number one, it's going to be difficult for me to kind of figure out where things are as I'm drawing along here, and I'm hoping that you could see everything as I go along. Also, again, because this is my first time, I would not expect a perfect lecture coming out of this, but this will be one for the archives of the first time doing this. One of the first times we're using this apparatus in the School of Business here. So what today's lecture is on is z-scores. So we're going to be defining z-scores. We're going to be going over the calculation. We're going to be working our way through a problem as we go through this to highlight what exactly a z-score is and why we would use it. A few things to keep in mind, or at least one thing to keep in mind. Students, the calculations for the z-score is very simple. All we're looking at is an observation minus the mean or the average divided by the standard deviation. So very simple calculation. And my phone just went off during my first session, so I'm just going to keep going. So the calculation itself is very simple, very straightforward. It's in the interpretation, I think, that students tend to get a little lost or a little fuzzy. So what I think the best way to illustrate what a z-score is, how we calculate it, how we use it, is to provide an example, and we'll kind of work our way through an example to illustrate the importance of the z-score and why we're going to use it. So in order to do that, we need to go back a little bit and talk about the empirical rule. Okay, so what I'm going to do is I'm just going to draw my normal bell curve here, okay? And I'm going to provide some data, and then we're going to do some inferences. As a matter of fact, I'm going to make this a little bigger for right now, because I really want to drive this point home and make sure, A, that you could see it, and B, that we're all on the same page here. So this is my normal distribution curve with the center line or the middle being my mean or my average. And I'm going to use a very specific example here. I'm going to use IQ scores, which I may have used in previous sessions before. I'm not sure, but the average IQ score is 100. So we have been taking IQ scores for the better part of 70 or 80 years now, so we have a lot of data collected on this. You may remember taking an IQ score when you were younger, and if we take all of these scores together and we do an average or a mean of all the IQ scores that ever have been taken, we are right at 100. Okay? We also know from those calculations that the standard deviation, I hope you can see that. I know there's a limit on this board of how high I could write. The standard deviation of all those IQ scores is 15. All right, so now we're going to do some very simple calculations based on the empirical rule, okay? And if you're not familiar with the empirical rule, I would highly suggest go back and look at some of the materials that I put into the course room. I have an open source type text that's in there that really does a good job of describing what the empirical rule is, but we'll go over it here real quick again too. Again, just to illustrate my point. So let's say we have a person who takes the eye, his name is Joe, and Joe scores a 115 on the IQ test. And then Joe goes, man, I wonder how many people I scored better than. What percent of the people, what proportion of the population have I scored better than with my score of 115? So let's just pick a spot out here where we think 115 would be, and it's somewhere probably around there. So what do we know? We know Joe scored better than the average, right? So we know he's on the plus side of average or better than average. Maybe we just don't know how much, though. If Joe's looking for the proportion of the population that he scored better than, well, there's some things we could use the empirical rule for to see how many he scored better than. The first thing we could look at is, well, if this is the average, and he scored better than all of these people here, everybody on this left side of the distribution curve. So in essence, we're looking at this area. If we shade all this area in, he scored better than all of them. Well, really what we're looking at is the area under the curve here. This is the area we're looking at under the curve. The area under the curve will tell us the proportion of the probability. This is the absolute direct midpoint. So if we say from here over would have to encompass exactly 50% of the population. So just looking at Joe's score, I could say, yeah, Joe, you scored better than 50% of the population. Actually, you did even better than that. But we're not sure what the area under this curve is, the area under this curve right here. Because if we add this area here, between this point and this point, to the 50%, we will find out how many people Joe, what proportion, not how many people, let me make sure I say that right. What proportion of the population Joe scored better than? What proportion of the population Joe scored better than? So all we need to do is figure out this area here under the curve. Okay. I'm going to erase some of the stuff I have here because it's going to confuse us somewhat if I leave it on there. Okay, so Joe had a score of 115. If you notice something interesting, one standard deviation equals 15. One standard deviation equals 15 points on an IQ score. So if I take 15 and add it to my average, I get 115, which is equal to one standard deviation above the mean. One standard deviation above the mean. It just so happened that he scored a 115, our standard deviation is 15. If we add a standard deviation to the mean, we get 115. All right, great. From there, we could figure out what the area under this curve is. How? We do that using the empirical rule. Because according to the empirical rule, one standard deviation above and one standard deviation below the average encompasses 68% of all observations. So one standard deviation above and one standard deviation below will encompass 68% of all observations. This is the empirical rule. There's a mighty big calculation in your statistics test books that demonstrate this or prove this, but we don't need to do that. We could say with confidence, we could say with certainty that 68% of all observations, no matter what it is that we're measuring, as long as the data is normally distributed, no matter what it is that we are measuring, 68% of all those observations will be between one standard deviation above and one standard deviation below the mean. So in this case, it'd be 115 and 85, right? If I took 15 from 100, I'd get 85, and that would encompass 68% of our observations. In other words, 68% of the people who take the IQ test score between an 85 and a 115. All right, so that's in essence what we're saying there. Okay, so how can I use this information now to figure out just this area under the curve here? I don't care about the whole thing. I just care, because I know this is 50% from here over. Well, this whole area here is 68%. From here to here is 68%. And since it's even, we would say this is 34%. And this side here is 34%. Okay, the whole thing is 68. This side's 34, and this side here is 34. Okay. Okay, so now we could figure out the calculation for Joe because he wanted to know what proportion of the population he scored greater than. If we take this 34% and add it to the 50% over here, because don't forget he scored better than everybody over here, not just. He didn't ask how many people scored between 85 and 115. He asked how many people did I score better than. So if this is 34 and this whole group of people here, the whole group of observations is 50% of all observations, it means that Joe scored better than 84% of all the people who took the IQ test. That's 50% plus 34%. He scored better than 84% of all the people who took the IQ test. Let's just stay a little bit. I want to make sure you understand this concept, and you may need to go back and look at this again when this one's done. This again, it's not an easy concept to grasp the first time, but I think the more you watch this, the more it might be. So let's assume Sue comes along and scores a 130. And Sue says, okay, what proportion of the population did I score better than? Again, this is very easy to figure out because one standard deviation is 15, and if we add 15 to that, it's 130. That's exactly 2 standard deviations away from the mean. It's not 2.5, it's not 2 1/3, it's exactly 2 standard deviations away from the mean. According to the empirical rule, if we go 2 standard deviations this way, and 2 standard deviations this way, so we're looking at this entire shaded area here. All the area under the curve here, that encompasses 95% of all observations. So going by the same rationale that we did with the 68% between 1 standard deviation, if we do 2 standard deviations, which encompasses 95%, that's 47, that's going to be too high to see. That's 47.5%. So from here to here is 47.5%. From here to here is 47.5%. Together, it's 95%. So Sue scored better than, don't forget, she scored better than all these people here. So we draw an arrow all the way back. She scored better than everybody from here to here. That would encompass 47.5% plus the 50% on this side, which is 97.5%. 97.5% of all people who took the IQ test score, Sue scored better than. And I think this is the point where you start talking about someone who's a genius at that 130, which means they're smarter, or they scored better, I don't know if they're smarter, they scored better than 97.5% of all people who took the IQ score. Okay, so again, that's very straightforward. This should be a very simple calculation for you to do as you're going through this. So, where does this get complicated? What if I said to you, okay, Matthew, and I'm going to start forgetting some of these names too, Matthew scored 120 on his IQ test score. He wants to know what proportion of the population he scored better than. I look up and I see, okay, 1 standard deviation from the mean is 115. 2 standard deviations is 130, but I don't know what 120 is. What proportion, what percent is that? There's no empirical rule that breaks down every single tick mark after 1 or 2 standard deviations. So fortunately, there's a standardized z-score calculation that we could do that could figure what proportion under the curve we're looking at. And again, that's what we're looking at, right? Whatever the area under the curve is going to tell us our proportion of the population. So the z calculation is going to tell us the proportion under the curve for that observation that we're looking at, okay? The observation. So let me draw my bell curve again. I'm going to try a different color. Since this is my first time, I'm going to see which color actually works better. Okay, there's our bell curve, and I've gotten pretty good at drawing these over the years. So our mean is 100, right? We did the average. We know the mean is 100. Matthew scored a 120 on his. And we still know from what we said before, the standard deviation is equal to 15. Okay, so Matthew's is a little greater than 1 standard deviation. So we know it should be a higher proportion than what Joe was, but less than what Sue did, because Sue was 2 standard deviations. So there was 97.5% of the population she did better than. Matthew isn't quite that high, but he's a little higher than Joe. So it's going to be somewhere in between there. Just that the empirical rule doesn't give us a nice, neat number for this. We have to do the calculation ourselves. And the calculation is a z-score calculation. And here is the z-score calculation, which looks a little, let me make sure I have this right, which might look a little odd, a little weird, but it's really very, very straightforward and simple. All it says is if we take the observation, so what is the observation? What have we observed in this example? Well, we observed that Matthew scored 120. That's our observation. And we subtract that from the mean and divide it by the standard deviation, which is 15, we get 120 minus 100. Oh, I'm drawing on my face. See, there's one of those examples where I want to watch. I don't want to draw in my face. 120 minus 100 divided by 15 equals, I'm going to make sure that 1.333 to infinity. 1.333. Okay, so our z-score, we're not done. We're not done yet. Our z-score equals 1.33. What does that mean? Well, it means that we're above one standard deviation, right? Because it's 1.3. So no, we're above one standard deviation, but we're not quite to 2 standard deviations because it's 1 point something. So 1.3. We're somewhere between 1 and 2 standard deviations, which yes, makes sense because we're at 120. This standardized 1.33 doesn't tell us much until we consult or go to the z-table. Now within the classroom I've attached a z-chart for you. And you can find a z-chart online anywhere. Just type in Google search z-charts and you'll find them. I happen to have one here in the back of my textbook, and I'll kind of show you what that looks like. I don't know if you're going to be able to see this very clearly through the screen, but this is what the z-chart looks like. And I'll talk you through this, and maybe the best thing to do is just kind of download the z-chart or go online and find one and follow along with me as I go through this. So we have a z-number of z-score of 1.333.